Inside your phone, your laptop, and nearly every piece of modern technology, there's a silent marvel at work: microchips. These tiny slabs of silicon are responsible for running everything from your favorite apps to life-saving hospital equipment. But while using a chip might feel like magic, the process of making one is closer to science fiction. To begin with, imagine trying to squeeze 90 billion transistors into something smaller than a fingernail. That's what modern chips pull off. It's a breathtaking display of engineering, a blend of physics, chemistry, robotics, and pure human determination. And it all begins with one ingredient: sand. Yes, the very same kind you find on beaches. Though not just any sand, quartzite, which is refined into pure silicon, the basis for every chip ever made. This silicon is melted down and formed into a large, single crystal ingot. Think of it like a log, only instead of wood, it's silicon so pure that any impurity would ruin its entire purpose. This log is then sliced into thin wafers about 0.75 millimeters thick, each destined to become the foundation for hundreds of microchips. Before anything else happens, these wafers go through intense cleaning. Why? Because even a single speck of dust, something invisible to the human eye, can destroy an entire chip. These wafers are handled with an almost obsessive level of care. They're moved using robotic arms sealed in specialized containers called FOUPs and transported on overhead tracks inside rooms that are cleaner than an operating theater. Once inside the clean room, the journey begins. Over the next 3 months, each wafer will undergo nearly 1,000 steps, moving from one gigantic machine to another. Some of these machines are the size of city buses and cost more than a luxury skyscraper apartment, up to $170 million apiece. The goal is simple but insanely difficult: build transistors and wire them together in a way that they perform logical operations, store data, and handle billions of instructions per second. The transistors, the heart of any chip, are built first. These aren't just on-off switches, they are nanoscopic gatekeepers. Today's chips use a design called FinFET, where the gate wraps around a raised silicon fin. These fins are measured in nanometers, 1/1,000,000th of a meter. For context, they're smaller than a red blood cell, smaller than a virus particle, and definitely smaller than anything the human eye can see. Making them requires a level of precision that feels superhuman. To craft just one layer of a chip, the process starts by coating the wafer with a light-sensitive chemical called photoresist. This step happens in a spinner, which evenly distributes the material. Then, the wafer is baked slightly to harden the resist. Now comes one of the most crucial steps: photolithography. Photolithography is a fancy word for what's basically high-precision stenciling using light. But instead of a flashlight and cardboard cutout, we're talking about extreme ultraviolet light in million-dollar optics. A blueprint of the chip's layer is projected onto the wafer. The exposed parts of the photoresist become weaker. The wafer is then developed, washing away the weak areas and revealing a pattern: the mask. This mask is used to guide the next step: etching. Etching removes the material where the mask allowed light to pass through. Think of it like carving microscopic highways into the wafer. These will later become paths for electricity to flow. Once etching is done, the mask is stripped away, and another material like copper is deposited. Then, the wafer is polished flat using a technique called CMP, chemical mechanical planarization. And that's just one layer. A full CPU might have 80 or more layers, each one requiring a unique mask and a full set of steps repeated over and over. Some of the layers are for logic, others for power delivery, and many are just there to route signals through the chip without interference. The deeper you go, the smaller the features. The top layers handle global communication, like highways. Mid-layers are local roads, and at the bottom you find back alleys, the smallest and most densely packed areas where core logic happens. Transistors themselves are so tiny and so packed together that a modern chip might house 26 billion on a single die. These aren't just crammed in randomly. They are arranged with a level of symmetry and logic that takes entire teams of engineers months, sometimes years, to design. As the wafer moves through the factory, every process is monitored constantly. Machines scan for defects with electron microscopes. Some tools inject individual atoms into the silicon lattice to form what are called P and N regions. This is ion implantation. Others deposit materials through chemical vapor deposition or physical vapor methods. Every type of material, from metals like copper and tantalum to insulators and doped silicon, has its own specific tool and process, and all of it must be exact. A slight deviation in temperature, timing, or even ambient vibration could ruin the entire batch. The tolerance is less than 1%. If something goes wrong, that means tens of thousands of chips could be defective. That's why every step is verified, double-checked, and then cleaned repeatedly. Cleaning tools wash wafers with ultra-pure water that's cleaner than medical-grade distilled water, drying them with filtered nitrogen or isopropyl alcohol. Once all the layers are done, and all the vias, those tiny vertical connectors between layers, are in place, it's time to test. Each chip on the wafer is checked for performance. Not all of them pass. Some might have minor defects due to dust particles or mask misalignments. But that doesn't mean they go to waste. The industry has a clever solution called binning. A chip with all cores working might be labeled a high-end i9 processor. One with a few non-functional cores might become an i5 or i3. Chips with defective graphics sections are sold without integrated GPUs. It's a smart way to use every bit of the silicon's potential. Nothing gets wasted unless it's truly beyond repair. After testing, it's time for slicing. A laser cuts the wafer into individual dies. These are flipped over and mounted onto a carrier called an interposer. This piece distributes electrical connections evenly and prepares the chip for final assembly. The chip is placed on a printed circuit board. It gets a heat spreader on top to manage temperature, then an integrated metal lid to protect it. All of this gets tested again. Only then is it ready to be placed into a retail box and sent to consumers, where it ends up inside a desktop computer, ready to power everything from spreadsheets to AAA video games. But there's more going on behind the scenes. To support the scale of modern production, semiconductor fabs are built to be unbelievably efficient. A typical fab might house 435 tools, processing up to 50,000 wafers per month. That's over 11 million chips monthly. The clean room alone spans the size of 8 football fields, kept at insanely strict environmental controls. Air is filtered constantly. Temperature and humidity are tightly regulated. Workers wear full-body suits to avoid contaminating the environment with something as simple as a flake of skin or a strand of hair. And all this effort, it's not just about making gadgets faster. It's about pushing the boundaries of physics. Every new generation of chips shrinks transistor sizes even further, from 10 nanometers to 7, then 5, and now even below 3 nanometers. At this scale, quantum effects start to kick in. Engineers must combat electron tunneling, heat dissipation, and signal interference, problems that didn't even exist just a decade ago. Even the tools used to make these chips are marvels themselves. Take EUV photolithography, for instance. Instead of visible or deep ultraviolet light, it uses light with a wavelength of just 13.5 nanometers. That's about 15 times smaller than previous tools, allowing for much finer detail. But EUV light can't travel through air or glass, so the system operates in a vacuum using complex mirror assemblies. Just the light source for one EUV machine can take up a whole room and cost tens of millions of dollars. And yes, these machines are fragile. A power fluctuation, a tiny misalignment, or even a brief glitch in temperature control can throw everything off, which is why these fabs are like temples of precision. As chips are packaged and boxed, they exit the clean room and enter the final phase of their transformation. The last rounds of testing are all about verifying reliability, thermal limits, and signal integrity. Remember, once these chips leave the fab, they'll be expected to function flawlessly for years inside devices that millions of people rely on. A final electrical test makes sure everything from cache memory to I/O pins works within expected parameters. Chips that pass get stamped, sorted, and loaded into trays. From there, they're boxed and shipped to motherboard manufacturers, data center partners, or directly to consumers. It's the last step of a process that began 3 months ago. Starting from a single disk of silicon, and ending with one of the most advanced machines humans have ever built. But this scale of precision doesn't come cheap. Building a state-of-the-art semiconductor fab costs upwards of $20 billion. That's more than the GDP of some small countries. And yet, for leading chip makers, it's a necessity. Why? Because the demand for faster, more efficient processors is insatiable. Smartphones, laptops, data centers, electric cars, even refrigerators. Modern life runs on silicon. And we're not just talking about consumer electronics. National security, healthcare systems, industrial automation, and even agriculture all depend on reliable chips. That's why the entire semiconductor industry is so fiercely competitive and, at times, geopolitically sensitive. Access to the tools, talent, and materials necessary for chip production defines which countries can innovate at the cutting edge. The global supply chain behind a single chip spans hundreds of companies across dozens of nations, from rare earth mining and gas purification to photolithography, tool manufacturing, and software design. And when disruptions happen, be it from pandemics, natural disasters, or political tensions, the impact ripples across industries. Everything slows down, prices climb, and innovations are delayed. The world learned this the hard way during the global chip shortage. Automakers halted production, phone launches were delayed, and GPU prices soared, all because a few tiny wafers couldn't get made fast enough. That's why investment in semiconductor infrastructure has become a global priority. Countries are building new fabs, training engineers, and incentivizing companies to localize production. At the heart of all this, though, remains the staggering complexity of the chips themselves. Take a moment to appreciate just how far microchips have come. In the 1970s, the first processors housed a few thousand transistors. Today's chips boast over 90 billion. And while Moore's law, the idea that transistor count doubles every 2 years, has slowed, the innovation hasn't. Instead of just shrinking transistors, chip makers are stacking them, layering them like skyscrapers, connecting them with microscopic tunnels, and pushing performance beyond what a flat chip could ever offer. 3D chip architectures are already here. Chiplets, modular blocks that get stitched together into larger processors, are becoming more common. And with AI accelerating demand for raw compute power, we're entering a new era where chips are no longer just better, they're specialized. There are chips designed solely for deep learning, image processing, encryption, and even autonomous vehicle decision-making. It's an evolution that goes hand in hand with advances in software, data processing, and machine learning. The lines between hardware and software are blurring. Designers no longer just think about circuits, they think about workloads. Chips aren't just faster, they're smarter, optimized for how humans and machines interact with data. And all of this, every leap forward, still depends on a process so fragile that a single dust particle can undo it. The next frontier is even more ambitious. Engineers are exploring materials beyond silicon, graphene, molybdenum disulfide, carbon nanotubes. Each offers potential beyond what silicon can handle. Faster electron mobility, better thermal performance, and the ability to work at atomic scales. These materials might one day enable chips that are even more efficient, powerful, and compact. But replacing silicon won't be easy. The entire global infrastructure is built around it: factories, tools, software, design workflows. To move beyond silicon would mean reinventing the wheel at every level of production. That's why the industry continues to push silicon to its absolute limits, and so far it hasn't disappointed. Alongside this technical progress is a fascinating ecosystem of collaboration. Scientists, physicists, chemists, materials experts, computer engineers, they all come together in a shared mission to build something that few truly understand, but everyone benefits from. Every chip is the result of decades of layered knowledge, of breakthroughs built on other breakthroughs. Even inside the factories, automation plays a critical role. AI systems manage scheduling, routing, and error detection. If a tool begins drifting out of spec, algorithms detect it before a human ever notices. Predictive maintenance, machine learning-powered inspection, and digital twins of production lines are no longer futuristic. They're standard practice. And then there's the question of scale. When 50,000 wafers are processed each month, containing hundreds of chips per wafer, the output reaches over 11 million CPUs monthly in a single fab. Multiply that by the number of fabs worldwide, and you realize just how prolific the industry has become. But with scale comes responsibility, environmental concerns, power usage, material sourcing. These are challenges the industry continues to grapple with. Chip fabs consume staggering amounts of electricity and ultra-pure water. Recycling, minimizing waste, and sourcing conflict-free materials have become core issues. And as chips become even more essential to modern life, the push to make their production sustainable intensifies. This is the fascinating contradiction at the heart of microchip manufacturing. A process so advanced it borders on magic, yet so demanding it requires constant vigilance, endless innovation, and the tightest tolerances of any industry on Earth. Still, every time someone unlocks their phone, starts their car, or loads up a new game, it all just works. The complexity disappears behind the interface. And maybe that's the most magical part of all, how something so complex becomes invisible, seamless, and ubiquitous. The next time a device powers on in seconds or streams video at lightning speed, there's a hidden world behind the screen, a world where physics meets precision engineering, where billion-dollar tools hum quietly in rooms cleaner than any hospital, and where silicon, shaped by light and logic, transforms into the soul of modern technology. And that wraps up the journey through the awe-inspiring world of microchip manufacturing. If this blew your mind even half as much as it did ours, now's the time to show some love. Hit that like button, share this with a tech-loving friend, and make sure you subscribe so you never miss the next deep dive into the marvels of modern engineering. And hey, if you want to go even further behind the scenes and support more videos like this, check out our Patreon community. Every bit of support helps bring these high-effort stories to life. Thanks for watching. See you in the next one.